Good afternoon, everyone. Today I'm going to discuss to you about reinforced concrete footing design. So still, we are going to discuss using BS 8110. So there are different modes of failure in the design of pad footing. So basically what we are going to discuss today is pad footing, or some could say it isolated footing, or like square footing, depending on different standards and books. Okay, so there are different modes, as I said, on the failure of the footing. So we have here, this one is when the failure is caused by wait when the failure is caused by the bending or flexion. So you have here, okay, this occurs here in this the face of the column. And then when the failure is caused by the transverse shear, this is at a d distance from this face of the column. Okay, so this is that area. And then by punching, you have at a certain distance, 1.5d from the face of the column. There's also the face shear, by which this column could be the location. The face of this column could be the location of the shear, okay, on the pad footing. So, for example, let's go straight to our example. So, example, you have here the load, dead load that is coming from your building is 1050 kilonewton. It could be like 3 floors or 4 floors, depending on the type of the building that you have. And then the imposed load or live load is still coming from the building that you are designing, is equal to 300 kilonewton. Now you set your assumptions, you set your criteria for your steel strength, yield strength 500, and then for the concrete, which is 35. So that depends on your design criteria that you have to assume. Okay, so the first is to compute for the plan area of the base. So, or the area of the base. Take note that you are going to consider a self-weight. For example, this is 130 kilonewton. It's somehow like 3 by 3 meters by 0.6. Okay, so that could be the size of your assumption. Your total dead load should be the load that you are carrying from the building, and then the self-weight of the footing. In this case, that becomes 1,180. Now, for you to get the area, the size of your footing, let us say you are looking at the top. This is the footing, and this is the column. Okay, so what would be the size of this one? For example, this is B and this is the L. Okay, to compute for the area, you need serviceability load, meaning it's an factored load. So your dead load and live load is just to be added without any factor. This is only one. Okay, so your 1480 becomes your N, which is reference to your computing for you to compute the area. Now you get the bearing capacity of the soil. That will depend on the type of the soil that you have. Let's say you have clay, silty clay, sand. So you check from certain standard. Here in Bahrain, you can check, or from in the Philippines, there's National Structural Code of the Philippines, or the American standards. Okay. So for example, the soil has a strength of 170 kilopascal, or this is kilonewton per square meter. Okay, this is the load kilonewton. When you divide 1480 by 170, this requires you an area of 8.7 square meters. Okay, again, 170, this actually you got this one from the soil bearing exploration, or you can get also from certain identified already identified soil, which will give you this bearing capacity. But obviously in the actual, you should be getting this one from the actual soil exploration. Okay, so we can assume our footing with a height of 600 millimeter or 0.6 meters. So for example, your area is 9 or 3 by 3. This is 9 square meter. This is meter times 24. You have 129.6 kilonewton, which is less than what you have assumed. Okay, so it's fine. Okay, so we'll see. Now, let us identify the ultimate load, okay, and then the earth pressure. So the ultimate load, you have now to multiply the factor of safety, which is 1.4 dead load and then 1.6 live load. Okay, before it's just a serviceability. Okay, so you have this one. Take note, in the earth pressure you can just omit, disregard this 130, so you can just have here 1050. You can disregard the self weight. Okay, so you have here the total of 1050 kilonewton is this load, and then this one is the area, which is a square meter I should say, and this is kilonewton, which will give you 217 kilopascal. Now this is now the pressure of the earth pressure that would push your footing up. Now, one mode of failure is this one. When this like cantilever, this become cantilever slab. When this one goes up, there is bending here. Okay, so if you see here, this is actually a total length of like 3 meters, right? But since the analysis of this one is just like this slab, we will just consider here like 1 meter. Okay, just like this slab, we will consider 1 meter. So how are you going to get this moment? So there is like the resultant load here is 217 multiplied by 1300, or 1.3. That becomes meter. This one is a millimeter. Okay, that becomes 1.3 with meter. So the moment, and then the moment arm here is 1.3 over 2. So you have here, okay, I'll just show you, 217 times 1.3 and then 1.3 over 2 multiplied by 1 meter width, so that you will have like this. Okay, that is how we can get this substitution. Okay, so our pressure moment here, kilonewton meter, is in terms of every meter width, meaning we consider only 1 meter width, just like your 1-way slab and 2-way slab. Okay, because after that you can identify the reinforcement in terms of spacing, not in terms of numbers or pieces. Okay, so this is the moment that you are going to get in identifying the reinforcing bars. Now, just like in the slab, you are going to check the MU. Okay, what would be the resisting moment or the capacity? Okay, so you have here, of course, the D, effective depth. You have H minus C. H is the total thickness. C is the concrete cover. We can use 50, and then just subtract with the diameter of the reinforcing bar. The diameter of the reinforcing bar that you are going to use is, we try to use 20 mm diameter. Okay, so we have this value of D, which is equal to 530 millimeter. Okay, so we have MU here. Okay, MU is 1500. This one 1534, which is greater than the design moment, which is only 183. In short, there is no compression reinforcement is required. This is similar to the single reinforced beam design. Okay, so when MU is greater than M, no compression reinforcement is required. So from that M, using this method, we compute K, we compute Z, and then we can compute AS. The required AS is 835 millimeters squared per meter, because we consider 1 meter width. Minimum requirement is 780. We have bigger value than the minimum requirement. So from this one, we can, let us say if we use 20, we can provide 1050, spacing of 300. So meaning our reinforcement is 20 diameter at 300 millimeter on center. Okay, so after this one, we check the punching shear. What is the punching shear? This footing is subjected to punching shear stress, meaning that this could punch this hole. Okay, this one hole could be removed. So it's just like when you have a footing like this. Okay, this is your footing in isometric. This one could be, this part could be removed. Okay, This part could be removed. Okay. Okay. So, okay, this one could be removed. So the distance of this one, we get the total area, we get this area, shaded area, so that we can calculate what would be the punching shear force, which is only subjected to this black shaded portion. So what is this? Okay, for example, here our dimension, well, we have 1.5D. This becomes 3D plus the size of this column is 400. So you have 3D plus 400. Now if you are going to get the perimeter of this one, because we are also going to calculate what would be the perimeter. Perimeter is just equal to 4. 4 of 3D plus 400. Okay. So you can have 4 of 3D. Okay. It's 3D and 400. Or you can follow this one. How many 400 do we have here? Here, 400. 1, 2, 3, 4. These are all 400. So you have 4 400 and then 8. How many 1.5D? There are 8 1.5D and then 1.5D. 1, 2, 3, 4, 5, 6, 7, 8. So you can just follow this one. Okay, 8 1.5D. So in all, total perimeter of this one is equivalent to 7960 millimeter or 7.96 meter. Okay, because we need this one later in computing the area subject to the punching shear. What is this area? Is this one. Take note that your shear force is going here. So this is the area that is parallel to the punching shear force. What is this? That area is just the perimeter multiplied by the effective depth. Okay, but first we have to identify what is this area, the shaded area. The shaded area is just, okay, 9. This is 3 by 3, which is the size of this footing, 3 and then 3, subtracted by this area with this punch hole. Okay, this punch hole. That punch hole is just, see, 3D by 400 plus 400 times 2. Times 3D times 400 squared, should say. 400 plus 3D squared. Okay, so if we are going to substitute it, 3D is 530. This is 530 we calculated earlier. Okay, this one. That D is 530. Square of 400 plus 3D will give you 3.96 times 10 to the power 6 square millimeter. So in square meter, this is 3.96 square meter. So the remaining area, the shaded part, is just 9 minus this hole or this area in the middle, that punched hole. You multiply it by 217. What is 217? This is the pressure, the earth pressure. Okay, this one. Okay, earth pressure that we have calculated earlier. So you will have here the punching shear force. Okay, punching shear force. We need this one to calculate what would be the design punching shear. The design punching shear is just equal to punching shear force over the P critical or the critical perimeter that we have already calculated, the 7960. Okay, just substitute 7960 and then D. This is the punching shear force, which is in Newton. This is in millimeter and this is in millimeter, so we can have here 0.26 Newton millimeter to the negative 2, or the same as like this. Okay, so I think you remember this one because in the table we need to calculate this part. Okay, for us to get what would be the design concrete shear stress, VC. Okay, I think you know this already from here. Okay, so in this case, this is 0.198, this is 0.198, and then our effective depth is more than 400. So it's in between 0.34 and 0.4. By interpolation, you can compute 0.37. And since your FCU is not 30, it's 35, you get the ratio between 35 and 25 to the power 1/3. So this is now the design concrete shear stress, 0.41. which is bigger than the actual. So meaning your slab, the depth of your slab is acceptable. So what happens if, for example, you have here, if this value is, let us say, 0.5, this is greater than 0.41, which 0.41 is this permissible. So what you do is you can just increase the value of D. Okay? You could move it up so that this one will be smaller. Okay, it should be that this value should be smaller than the allowable. You have your allowable, this one is the actual shear stress. Okay, so that is for the punching shear stress. Now the next one is for the face shear. Face shear is only in this portion. Okay, so you just need this W. What is this W? The one that you have calculated earlier, this one in the design moment. Okay, this is 1950, substitute it here. Okay, and then the column perimeter. The perimeter of the column is just, this is the column, right? 400, 400. So just 4 times 400, then effective depth. This one should be less than the permissible. Permissible 0.8 of what is this? FCU. The value is 4.73, so meaning this one is fine. Okay, it will not, the footing will not fail in the face shear. Again, if this one is bigger than 4.73, you have to increase the value of D. Okay, the other one is the transverse shear. Transverse shear happened when the footing fails at D distance of the column, meaning this one will be removed. Okay, this part will be removed. So if you're to look your footing, it goes like this. Okay, at this part it could be removed, and that distance is 770. Of course, this is D is 530. Actually, the total here is like 1,300. So 770 and 530 is 1,300. Okay, so this one is 770. This distance is 770. So how do you get the area? The shear force. Okay, the shear force is just 217, our earth pressure, and the area. What is this area? This shaded area. This is 3, and this 0.77. So you have 3 and 0.77. So you have here the transverse shear force. To compute for the design shear stress, what do you do? The transverse shear force, which is this one, 501 kilonewton, now it becomes Newton. B, this is this one, 3 meters or 3,000 millimeter, and then effective depth. So you get 0.32. Again, your VC, which you calculated before, is 0.41. This one, okay, if you remember the first slide here, okay, 0.41. Okay, so 0.32 is less than 0.41, so it's fine. Again, if this, meaning there is no shear reinforcement. Otherwise, if it's bigger, there's a need of shear reinforcement. You have to calculate for a shear reinforcement, or you can increase again value of D to make just to avoid shear reinforcement. Okay, so this is the case that would be possibly happen if you are going to have like V is greater than VC, and then you calculate your value of your shear reinforcement. Or again, as I said, to avoid shear reinforcement, you can just increase the value of D. Okay, and then you come up with your reinforcement details. You just follow this one. Of course, you have to provide here the thickness. Thickness is 600 or H. Okay, now if you have to change the D, effective depth, if you change this one, of course H will also be changed. So I think that's all for this video. Thank you, and see you in the next video.